Okay, now let's talk about what actually makes motion happen. Let's talk about Newton's first law. Let's also introduce the concept of inertia. So in this chapter, we'll kind of start off with what we used to think was true. So, starting with a Greek philosopher around 300 BC, what he thought motion was about. And that concept lasted for about 2,000 years until Galileo came up with this concept of inertia, so we'll talk about what that is. That kind of led into Newton's first law of motion, which relates forces to changes in velocity or acceleration. So we'll talk about net force and a special case when the net force is equal to zero, called the equilibrium rule. We'll talk about the support force and how things that are moving can be in equilibrium. So just a little bit of history. When we start talking about motion, it started around 340 BC with a Greek philosopher by the name of Aristotle, and he said any object not in its proper place is going to seek it. So, for example, stones are going to fall down to the ground because that's their natural place. If you have a rock up here and the ground down here, well, it's going to fall down. So right here must be its natural place. Let's think about something like smoke. Smoke is going to rise, right? If this is the ground and you have a little puff of smoke, then it's going to go up, kind of like that. So its natural place must be up there somewhere. He also said that natural motion is going to be straight lines on Earth, so rocks are going to fall down in a straight line. And outside of Earth, then it's going to be circles. And for example, if this is the Earth, then obviously the sun goes around the Earth just like that. And of course we do know that that is wrong. He also had this idea that an object's velocity is going to be proportional to the force that is on it. So more force means more velocity, and it turns out that that idea was also incorrect. Interestingly enough, these ideas lasted for about 2,000 years. It wasn't until Galileo in the 1500s demolished Aristotle's assertions. For example, if speed was proportional to force, then if we had two balls with different mass, this ball and this ball, well, this ball right here has more force, and so it should fall at a faster rate, and obviously it does not. You saw me do that demonstration in the previous lecture. So he kind of discovered that different weights, they're going to land at the same time. And he also found out that a moving object doesn't need any force to keep it moving, which was contrary to what Aristotle thought. So kind of coming back to his ramps, what he kind of knew is that if you had a downward sloped ramp, then the speed is going to increase. And if you had an upward sloped ramp, then speed is going to decrease. So what he kind of reasoned is somewhere in between, if we had no slope, should the speed change? And the answer is going to be a big fat no. And he said, well, what keeps this going? Big old question, why? Well, it turns out that a moving ball is going to have this thing called inertia, which is going to keep it going. And inertia is not going to be a force. So what exactly is inertia? Inertia is just a property of matter that's going to resist changes in motion. So you could also think of inertia as the fact that things are lazy. Objects want to keep on doing what they're doing. If an object is at rest, it wants to stay at rest. If an object is in motion, it wants to stay in motion. And how much inertia an object has is going to depend on the amount of matter or its mass. So let's just kind of think of this. Suppose your car breaks down and it has a speed of 0, or let's just say you ran out of gas and you want to go ahead and you want to push this thing to a gas station, then sure, it'll be hard, but you can probably do it. Now, if you're in a Mack truck and it breaks down and it has no speed, you want to push it to a gas station, well, that's a whole heck of a lot harder. Now, why is that? Because this object has a lot of mass. This object doesn't have a lot of mass. So this object right here has a lot of inertia. This object does not have a lot of inertia. And it works the other way as well. If this object right here, if your car is in motion, then okay, you can stop it. If a dump truck is in motion, well, I don't know about you all, but I'd much rather try to stop my car in motion than a dump truck in motion. So more mass, more inertia. Some examples of inertia would be this beaker full of water. It's sitting there. It wants to remain sitting there, and so it doesn't follow the paper. Same with this pile of coins. They're at rest. They want to remain at rest. A more challenging example would be this one right here. You're not going to see me attempt this, but these eggs are at rest. They tend to want to remain at rest, and so they go down into their respective glasses. Another example would be seatbelts. If we don't have seatbelts, then our body is in motion. It's going quite fast. We would just keep on doing what we're doing, which would not be good for us, obviously, as you can see from this YouTube video. If we do have seatbelts on, you can kind of see that the seatbelt's going to keep us from crashing into things. The same is true for headrests. Why we have headrests, it's in case you get into a rear-end collision. As you can see right here, the head is sitting there. It tends to want to remain sitting there, and so we put a headrest there so our neck doesn't snap back like that. All of these are examples of inertia. So let's just take a second and think about this question right here. So which one of these is the most true? Well, let's see. It did not eliminate the acceleration due to free fall. It slowed it down, but it didn't eliminate it. I haven't talked about energy yet, so the answer to this one is going to be C. Now, this fellow by the name of Isaac Newton came along about 50 years after Galileo, and he kind of took this idea of inertia, and he took it just a tiny step further. And what he says is an object is going to continue in a state of rest or at a uniform speed in a straight line unless acted upon by a non-zero net force. And net force is kind of what Galileo was kind of missing. So the first part of this is pretty much saying inertia. An object's going to keep on doing what it's doing. It's going to stay at rest if it's at rest, or it's going to keep on moving in a straight line at uniform speed. So it's just going to keep on doing what it's doing. It has inertia. Now, this idea of a net force, let's talk about what a force is. A force is essentially going to be a push or a pull, and it turns out that this friction force is what threw Aristotle off. It was this force due to friction that caused objects that were rolling to eventually slow down and come to rest in what Aristotle thought was their natural place. Now, let's talk about this idea of net force really quick. Net force is going to be kind of the sum of all the forces on an object, and it's going to be a vector quantity. So if I have an object like this, and I have a force in that direction, and I have a force in that direction, then the net force is just going to be, the sum of all those forces. And if this one was just a little bit longer, then the net force we would say is in that direction. Now, let's just talk about forces for a minute. When I talk about a force, it's going to have a unit of a newton, so a capital N. So if you see anything with an N, that's going to be a unit of Newton. And again, this is going to be a vector quantity, so direction kind of matters. If we call this the positive side and this the negative side, or left and right if you will, then it really does matter whether you have forces pulling to the left or to the right. And as with all vectors, kind of how long they are going to represent the magnitude, and the arrow is going to show the direction. So let's just get a little bit of practice calculating some net force, and again, that's just going to be a combination of all the forces that act on an object. So let's just take a look at this example right here. If we have two 5 Newton forces, force 1 and force 2, both directed towards the right, then the net force is going to be simply 10 newtons in that direction right there. We have 5 newtons to the left and 5 newtons to the right, or vice versa. Then they're going to cancel out, so this is the classic tug of war, and the net force would be 0 newtons. And do yourself a favor, just pause this guy and see what you think. Suppose you have a cart and you have a force to the right of 15 newtons and a force to the left, this guy a little bit longer, of 20 newtons. Then the question you would ask yourself, what is the net force acting on the object? Then we would expect it just to be 5 newtons to the left, so it's going to be this guy right here. And just a little bit more practice. Suppose you have a box shown as the one right down here. What is the net force acting on the box? Obviously this one is stronger, so it's going to win, and they're going to subtract, and we're left with 5 newtons to the right, so it's going to be this guy right here. Now, something just to keep in the back of your head is that force is going to be a vector, so it could be in 2 dimensions. So for example, suppose we have a girl hanging by a rope, and what's pulling her down is going to be her weight, or her mass times gravity. and there's going to be some tension in the left-hand rope, so there's going to be some tension in this rope right here, there's going to be some tension in this rope right here, and kind of all of these guys are balancing each other out in both the x and the y directions. So these two guys right here, these two guys in green, are going to kind of add together to make a vector that's going to essentially support her weight. And you might ask yourself, well, which side is going to have greater tension? In your mind's eye, it would probably be this guy right here, simply because the rope is at a steeper angle. Perhaps another example of this is, suppose we had an angry professor sitting in a chair, and he had two students pulling on him with ropes, one pulling in this direction right here, and one pulling in that direction right there. And what we can kind of do is we can kind of say, well, we care about the front, right, or up, down, left, right directions. So we care about these directions right here. And what we can kind of do is we can kind of break that force up into a component like that and a component like this. We can kind of break this guy up into the two components as well. And if the two students pulled with equal amount of force at equal angles, then kind of symmetry would convince you that this force right here and this force right here would essentially cancel itself out, and the professor wouldn't move to the left or to the right, but this force right here and this force right here would essentially add together, and we would have some big net force in that direction, and the angry professor would go off in the upwards direction.